This is my implementation of the weighted dots and boxes assignment. So to represent the game state, I modeled it as a list of boxes, each comprised of booleans for each of the edges, a weight, and a integer representing who owns the box. Because a lot of those edges are redundant, I maintained a dictionary that maintained the equivalence between all of them, and because that would be a lot of things to track, I also maintained a list of valid moves that is not redundant. I've got a function to fill in an edge. It checks both the box of that edge and its equivalent edge, and then calls the checkbox function. If the box will then be filled, it updates the score based on whoever's turn it is. I've got a display board function that just builds a string representation of the state of the game, prints out the dots, the edges, the boxes. If a box has been claimed, it replaces the value with a P for the player, C for the computer. And then just a little boolean check to see if there are any possible moves left. On the player's turn, it takes a move as input, makes that move, and on the AI turn, it calls the search function and then makes the move that results. Alright, so this is my minimax algorithm using alpha beta pruning. When it starts up, initializes alpha and beta to negative and positive infinity as far as our game is concerned, and then searches through all of the available actions and takes the minimum value for each action and passes it that alpha and beta value. Then the minimum value initializes that action to infinity, and then searches through its options and takes the max. When we go to the max, set our value to negative infinity. Well, let's just say that this is an end node, and it returns a value up here. That value is certainly going to be less than infinity, and so it sets that as its new lower bound and continues checking. So if any of those values that it finds are less than that, that will be the new V, and it will eventually return that to the top. And the max value is doing just the opposite. If you've got a max value with a tree of mins below it, it's got an alpha and a beta. And this beta corresponds to the minimum value of its parent. So if it encounters a value that is greater than that, it knows that it will never be selected by the min above it in the tree, and it can just stop searching and return its current maximum. And the min value is doing the same thing here. If it has a value that's less than the alpha, which corresponds to the max above it, then max will never select that value, and it can prune the rest of the nodes there. And this here's my main. It just runs the game, alternates turns until there are no moves left. And there you go. Just for time's sake, 2 columns, 2 rows, and 4 plies. I'm just going to go in the top left corner. It chooses to go there. 1, 1. Let's go bottom right. He's going to keep playing around. Go 0, 1, 2. Just notice he's refusing to make a move that would allow me to score. And I am doing the same, so now let's give him the least score that we can give him here. 1, 1, 0. So he's going to take the 4, and I have to take the 1, and then he clips the rest of them.